Hi Year 9s, this is your video, your guidance video for section 10.3, changing the rate of a reaction part 1. This is week 12's work, and by the end of this lesson you'll be able to tackle questions like this question that appeared in June 2019. So this was a metal carbonate reacting, this is actually magnesium carbonate, reacting with nitric acid. I certainly hope that you know by now that magnesium carbonate reacting with nitric acid will form a nitrate salt. So the actual salt is magnesium nitrate. And because it's a metal carbonate, you form carbon dioxide and water as the two other products. But that's not the most important part of the question. The most important part of the question comes for today's lesson comes in part 4 and part 5 of that actual exam question. It talks about how does increase in the temperature affect the rate of this reaction, and how does decreasing the concentration of the actual acid affect the rate of this reaction, which can be quite a confusing question to tackle first on. So we do need to know how temperature affects the rate of a reaction and how concentration affects it as well. Now, you've got to be quite clear about one aspect. When we're talking about changing the rate of reaction, changing the speed, if you want to think about that as of a reaction, this doesn't actually tell you anything about making more product, okay? In order to make more product in a chemical reaction, you actually have to have more of both reactants, okay? More of both reactants. In a case where you would actually have something like the experiment that we looked at in our previous week, here we have 0.05 grams of magnesium. This is very familiar to you, I hope now, because we looked at this extensively last week. It was magnesium that was reacting with hydrochloric acid, and in this situation, the acid is in excess. So what happens in this chemical reaction is that all of the 0.05 grams of magnesium will be used up. You form hydrogen gas. This gas syringe is going to move slowly towards the right, because it's going to contain the volume of that hydrogen gas. Now, this acid is in excess for the first experiment, and it just so happens that if we repeat the reaction and we double the concentration of this acid, it will also be in excess. What do we mean by excess? Just to quickly remind you, when you have something in excess, when you actually have a chemical reaction taking place between something like magnesium and something like this acid, which is in excess, the magnesium will be completely used up, okay? You will have some of the acid particles left over. If there's more acid particles, then there are magnesium particles to react with it. Okay, so that's what's meant by excess. So in both situations here, we actually have two experiments where you have acids in excess. But in the second one, we actually have twice the concentration. And what do we mean by twice the concentration? Well, essentially, in this 50 centimeters cubed of acid, which is the same volume of the acid as you have in the first example, A. So in B, you actually have double the number of positive hydrogen ions reacting or ready to react with the magnesium. So as a result of that, because you've got double the number of particles that are present, you would expect there to be less time to be taken for an acid particle to hit magnesium. As a result of that, because you've got more acid particles, twice as many in that volume, the chances of having a successful collision are doubled. Remember, it's not always the case that when you have an acid particle bumping into a magnesium particle, you have a successful chemical reaction. It has to actually be traveling towards the magnesium with a sufficient amount of energy as well. So we are expecting there to be a greater success rate of reaction between the acid particle and the magnesium over a given period of time because there are twice as many acid particles present in B compared to A. So there's double, so the chances are double. Now, when we look at the results of this experiment, the curve should actually be familiar because we actually were able to look at that to a great extent in the lessons before the Eid holiday. But here we actually have two different curves. Now, basically what happened was, this is actually a plot. You've got the volume of hydrogen on the y-axis, that's what's being measured, and you've got the time in seconds, that's just passing along, that's at the bottom over here, okay? So because you've got, if we were trying to figure out what the rate of a chemical reaction would be, the rate of reaction is equal to the change in the amount of product divided by time. So the change in the amount of product, which is what you would find on this axis, divided by the change in time, which is this axis over here. Now that is pretty much the gradient at any part of this on this graph. So we have a look, like say for example over here, this gradient, the slope of this part of the graph over here is much steeper than the slope is over here. So we actually can see that, say for example, at the 20-second mark, you can see that the slope of the graph of volume versus time, or time versus volume, I should say, is actually flatter. So the rate of reaction with experiment A at the 20-second mark is actually lower than the rate of reaction at the 20-second mark of B. Okay. Now, what does this mean? Well, if the rate of reaction is lower in A at that point in time, compared to the 20-second point in experiment B, that means that A was producing less gas at that moment in time, in those time intervals, compared to experiment B in that time interval as well. So the reaction in A was actually much slower than the reaction in B. Now, what we can actually see is that, so let's just focus on what happened in experiment A. So in experiment A, you can see that the chemical reaction was taking place. It was taking place. Let's just change the ink color just to make it clearer. It was taking place. It was running. It was running. It was running. And then the magnesium was starting to run out. The acid was still there because it was in excess, but the magnesium was running out. So it was taking longer and longer for the acid to actually reach the magnesium. And eventually, at this point over here, which is roughly, let's say, it's more accurately over here, roughly around about the 120-second mark, that's when all of the magnesium was used up. And we know that because no more hydrogen was actually produced. If the hydrogen was produced, then this line would actually keep going up, but it's not. Now, in experiment B, because there were twice as many acid particles, the chances of successful collisions between the acid and the magnesium was much greater. So the magnesium, looks as if the magnesium was being used up at a much faster rate, okay? And it was only right up until 60 seconds in this reaction that we actually had hydrogen being produced, okay? Once 60 seconds had passed, the volume of hydrogen was actually fixed at 60 centimeters cubed, okay? So at that point, the reaction had finished. So what we can deduce from this is, first and foremost, that both reactions produce 60 centimeters cubed of hydrogen. That's a given fact. And what we can also do is we can actually figure out what the average rate, because the curve is, because there is a curve and because it's constantly decreasing in gradient, we can't actually say, with a surety that, we can't compare the rates. But what we can do is we can say, right, well, after around about the 120-second mark, for experiment A, the time taken was 120 seconds, and the volume of hydrogen produced was 60 centimeters cubed. Okay, so it was 60 centimeters cubed by 120, and that means to say that you've got an average of 0.5. So it's centimeters cubed per second. That's the average mean reaction rate over the course of the chemical reaction in experiment A. Now in experiment B, the volume was again was 60 centimeters cubed, but the time in this situation was 60. Okay, so the mean average rate was 60 divided by 60, which is actually equal to 1, and the units would be again centimeters cubed per second. Okay, so you can actually compare the 1 with the 0.5, and you can see that there is a difference. Okay, there's basically when you use twice the concentration of the acid in experiment B, you actually have a mean average rate which is double the reaction rate in experiment A. And that's a really nice conclusion to draw. In this example, doubling the concentration doubles the actual rate of a reaction. So these results show that a reaction definitely goes faster when the concentration of a reactant is increased. Now, if we go back to our exam question, we can actually look at this. It says, how does decrease in the concentration of the acid affect the rate of reaction? Well, we just learned that increase in the concentration increases the rate of reaction. So as long as all other conditions are kept the same, decrease in the concentration, so we can write in decreasing the concentration decreases the rate of reaction. Okay, so that would secure us 1 mark. Okay, now what we're going to do is we're going to look at temperature. Okay, so there is a YouTube video that I have located for you. It's something that's been made just like last month or a month and a bit ago. So it's quite a new one, and it talks to you about an experiment. I can't reproduce this experiment, unfortunately, with distance learning. But the two reactants are hydrochloric acid and sodium thiosulfate, and basically the concentration of both of these solutions is kept the same, and this actual reaction is slightly technical reaction in the sense that you do produce quite a few products. So you don't. And the good news is that you don't actually have to understand or recall the actual equation, but what you do need to appreciate is that one of the products is an insoluble yellow precipitate called sulfur. So when you have dilute hydrochloric acid reacting with sodium thiosulfate solution, that actually makes a yellow precipitate called sulfur. Let's keep it yellow here, okay? Now, the two solutions, I should say, hydrochloric acid and sodium thiosulfate, those are actually colorless solutions. Okay, so when you look at them, there's no color at all. But what actually happens is when you add both of the solutions together, so you have two colorless solutions. When you add both of them together, here we go. After a certain amount of time, what happens is that it starts to cloud over. Okay, so it starts to cloud over. It's not instantaneous, but it can be within. You can actually get it within 10 seconds, depending on what conditions you choose. So basically, we can actually utilize this. Now, over here, you can see that the shot of the video over here shows you a beaker. Now, this would actually have both of the solutions added into the beaker, and you would get eventually you would get like this yellow sulfur forming. As soon as a certain amount of sulfur forms, you can't actually see through the solution. So that's a really good indication of how quickly the chemical reaction is going, how quickly the rate of reaction is going. Because when you get to a point where you cannot actually see through the solution, you've got a certain amount of product that's actually being formed in there. Okay, so what we can do is we can actually utilize that by drawing a cross on a white background and putting it underneath our reacting solutions. Okay, so once the reacting solutions get to a certain stage, the reaction takes place. Slowly but surely, you form this yellow sulfur, and after a certain amount of time, it just clouds over. Okay, until eventually, what you do as an observer is you stop the clock when you cannot see the cross at all. Okay, so the cross goes fainter and fainter as this insoluble yellow precipitate forms. As soon as the observer looking right from the top cannot see any of this cross, they stop the timer, and that gives you an indication of the time. So the faster the cross disappears, the more the amount of sulfur product is formed, and as a result, so as faster the cross disappears, the quicker this cross disappears, because you're forming more of the sulfur, and the faster the rate of reaction. Okay, so what you can do is you can actually keep the concentrations of both of these exactly the same, but what you can do is you can raise the temperature. So if you raise the temperature and keep the concentrations the same and keep everything else the same, the volumes the same, etc., what you can actually do is you can then track how the temperature changes affects the time it takes for the cross to disappear. And here is a typical table, and this is a table that's in your book as well, so you can actually see temperatures that were chosen were 20, 30, 40, 50, and 60. So it's a typical table here, and what you'll need to do is you'll need to be able to interpret this. So you can actually see that the time for the cross to disappear in seconds at the 20 mark was roughly around about 200 seconds. And then what happened was when you increased it to 30, the time went down to 125 because the reaction rate was much faster. 40 got it down to 50, and then 50, 33, 60, 24. So the higher the temperature, the faster this actual cross disappears. Now, there's an interesting pattern that you can actually see even within these this table. The cross disappears when enough sulfur has fallen behind it. It took 200 seconds at 20, but only 50 seconds at 40 degrees. Okay, so basically, it took a quarter of the time for the reaction to get to that stage when you increase the temperature by 20 degrees, okay? So it took a quarter of the time, okay? It took roughly around about half the time when you actually increased it by just 10 degrees, okay? Now, in chemical reactions, what we often find, particularly, and we use this in industry and as well as cooking, a reaction goes faster when the temperature is raised, but when the temperature increases by 10 degrees, generally you get a rate that's doubling. Okay, that's just a pattern that we see across all chemical reactions. Okay, so it's the reason why we use pressure cookers in our traditional methods of cooking. Okay, so here's a pressure cooker. Okay, so when we use a pressure cooker can actually heat up foods to 125 degrees centigrade, right? So 125 degrees centigrade is 20 degrees above the boiling point of water. Okay, so if you've got a cooking time of, like, say, for example, 1 hour when you're cooking some vegetables and you're boiling some vegetables at 100 degrees centigrade, that cooking time will halve if you take that temperature up to 110. It will halve again to a quarter of an hour if you take it up to 120 degrees. Okay, so you can actually decrease cooking times by an extensive amount. Now I'm going to finish off with going back to that original question. So in the first part of the question, we can actually see how does increase in the temperature affect the rate of the reaction? All other conditions are kept the same. So now we can actually utilize that fact that we've just learned for every 10 degree rise in temperature, reaction rate doubles. Okay, All right. So the most important point for that, you could actually just sort of say when you raise the temperature, when the temperature is increased, reaction rate doubles. But now we've actually got something which is really, really cool. We've actually got a trend that we can identify as well. Okay, so those are the answers. Increased rate goes faster is absolutely fine. Decreased rate goes slower when you are decreasing the concentration. Okay, and I'm going to finish off with this question over here. This was by popular demand. People wanted to know how to do more questions in my videos, and it makes it much easier for others watching the video from around the world to actually gain benefit from this. So here is a student investigating the reaction between zinc and sulfuric acid, 20 degrees. So that's our little alarm, right? This is talking about temperature and rates of reaction. The zinc was in excess. So if the zinc is in excess, that means that we're going to be running out of sulfuric acid particles, okay? Remember, sulfuric acid, H2SO4, and it's a source of H plus positive hydrogen particles, right? Okay, this reaction will form hydrogen gas. Okay, what should the student do to start the reaction? Well, you may not notice, but there is actually a little tap over here. Okay, it's a little tap. So what they need to do is they need to open the tap. Okay, all right. So this little flask over here, this apparatus, it keeps the acid in this space over here, but there is a tap. Okay, there's a little tap there. So open the tap, and that's what gets you started on the chemical reaction. Okay, right. So this question is actually from 2016, the core paper. This question included a graph. It shows the volume of hydrogen released as the reaction proceeds. So here we go. There's the volume of hydrogen here, and then you've got your time in minutes on the x-axis there. Okay, so volume of hydrogen up here, centimeters cubed, time in minutes. So it was seconds before in the examples, now it's minutes. Okay, so the student repeated the experiment at 30. Now immediately what you have to do is you have to think, right, repeated the experiment at 30, all other conditions remain the same. So that means the only thing that's changing is perhaps temperature. Okay, now you need to look back. You need to think, right, okay, what was the original temperature in the experiment? Well, it was 20. So might help for you to just when you're doing the exam to actually just annotate above there that you're increasing temperature. You need to talk about an increase in temperature and what the effect is on the rate of a reaction. Now, what does increase in temperature do? Okay, so with a 10 degree temperature rise, we learn that the rate of reaction doubles. Okay, rate of reaction doubles. All right, so if the rate of reaction doubles with a 10 degree rise, we can actually do this. So if the rate of reaction doubles, that means that the gradient, when the reaction is happening and it's taking place and all the particles are bashing together, the gradient actually doubles as well. Okay, so if the rate of reaction doubles, that means that this gradient over here is going to double as well. So the first thing that you need to do is you need to make sure that you start at the 0, 0 mark. Okay, so start here. Start your line there. Okay, so start from here. Make sure you're starting at the 0, 0 and make sure that it looks as if it's double. Okay, double the height. Now you can just mentally do this by thinking, right, okay, well, where's the 10 for this one? And the 10 hits it there. So at the same point, you should have your line going through 20. Now, remember the fact that I shared with you right at the very beginning. When you're changing conditions, you're not actually changing the amount of product unless you're changing both the products itself. So remember, all other conditions remain the same. You've got the zinc in excess. The acid is there, so you're not adding more acid. Okay, you're not going to get more hydrogen. Okay, so as a result, let's just have a look over here where this line is, that's where it should, and you should have both lines basically joining there. Okay, so let's just continue the line, and it should end there. Okay, here we go. I'm just limited by the hardware that I'm doing, but doing the best job that I can. Okay, and that would be acceptable. Yeah, just looking along across the line, just double check that. And if you do it in pencil, then you probably want to just ease up that bit there. and then that's basically the shape of the line on the grid that you would need to do. Okay, hope you got that, because the answers, there's the open the tap answer that we had, so that's absolutely fine. The line is steeper than the line of steeper gradient, the line that you draw must have a steeper gradient, so we've got that, and it must start at 0, 0, so we've got that. Both points are linked together. And finally, the line ends at the same volume as the one drawn on the grid, but reaches this volume sooner, and we've got that as well. So both marks absolutely in the bag. I hope that you've enjoyed this introductory video that I've done in this very new format. Changing the rate of reaction, thinking about how temperature affects. Remember that we've just learned that as you get a 10-degree rise in temperature, you're expecting the rate of reaction to be doubled, assuming that all other conditions are kept the same. And then if you increase the concentration, you also of reactants, you would tend to find that you increase the reaction rate as well. But remember that the rate doesn't affect the amount of product that you get. Thanks for watching, and stay safe and stay at home. All you'll need to do, by the way, is you'll just need to complete the quizzes that I will set through the Google Classroom. And thanks very much for watching if you're watching from outside. Bye for now.